Yeah, I'm ZhiHong, and you can see Liang also, and you will see Liang later on the stage, I guess. So this topic is about the virtual switch upgrade, which is actually a ancient topic. During the years, people have proved that there are many ways to do that, and today we're going to share our way to optimize that. And so here is the content. First, we're gonna some quick background introduction, like why did we do this, right? Is it really necessary to do this? And then we will share all the details. Okay, let's get started. First, some quick background. So first of all, nowadays that we know there's a lot of offload. There's quite a few offload solutions already, and but they're good and they have good performance. And in the meantime, the software virtual switch still has its unique merits, such as it's stable, it's out of the box, and for the agility, we can easily to develop some features, and also the performance. We need to mention is it's also increasing during the years. They have good performance, good enough performance to cover quite a lot of scenarios. So another background is about the Vhost-user. This part that I'm going to just quickly talk about, like the Virtual. We know the Virtual net. It has some like all enough basic features we need, and it also has a lot of features for example like migration. It has good support there. And also the performance of it, we have seen performance improvement during the years, such as first of all the CPU is running faster, and also we can do like macro architecture level optimization there, especially for memory copy, like for different architectures, and also like there are different other technologies coming, like the DMA engines, those stuff, they're in the community right now. So all this suggests that software virtual switch still can cover a lot of scenarios, and sometimes they have just the good TCO there, and just to ensure we can meet all the good stuff we just mentioned, such as agility and good to maintain and those stuff. We really need the rapid iterative development model. So to make sure of that, upgrade is really necessary. It's almost mandatory. So when we start to design the upgrade solution, the objective is very simple. So first of all, it's going to be really, really reliable, because that's the bottom line, right? Like it's going to be able to run like millions of times correctly and handle various situations. And then secondly, it need to be guest unaware. That's also very important, because we're really gonna run that. There's gonna be tens of thousands of servers, and if we cannot do the next thing otherwise, if every time we do an upgrade, the guest will see network card down and up, and the network blackout for several seconds, that's gonna be a total disaster. So the second is gonna be guest unaware, and then of course it's gonna be flexible. That's why we do upgrade, is to allow necessary changes to different part of the program. So that's 3 parts. And to just talk a little bit about the process. The path we choose is to do process iteration, which means when we have an old process running, and then we start the new process by side, and then we just sync and transfer everything needed from the old process to the new one. And then the new one can take over and the old one can quit. So just list a few here, like the sessions and also the data path. The sessions they can do in parallel, like the old ones can still be functioning, and then we can sync the sessions and just in the meantime. And for the lead card, the data traffic from the file, we can we can use VFs, or we can use like traffic duplication. Those technologies can solve that part. But one part of that is a little bit tricky, which is the link, the data path between vHost and the virtual machines, QEMU and the virtual driver. Of course, we naturally we can just disconnect. The old one can quit, and then the new one can start talking to the QEMU, and everything, just redo the negotiation process. Everything goes back normally. But that one, as we showed here, it's a little bit time consuming, and so obviously this one is quite reliable. This process is very reliable. Basically, they reduce all the negotiation process, and this one is also flexible. Basically, the old one does not need to care about the new process. But the downtime is a bit unbearable. We can, and here it's the number we showed. Like we tried from tens to hundreds of reports. The total downtime can be like 2 to 5 seconds. So if it's just one time, then it's okay. But if we do this from time to time and to like hundreds of thousands of servers, that's going to be unacceptable. Okay. So naturally we try to optimize the downtime, and to make sure that the guest is unaware. Basically, we can the way we can think is that make the just to take out the renegotiation process. Like if you just keep the because between the virtual and the host, it shares all the memory stack and also the FDs, right? And just to make sure that the new process can also have those information, and then you can rebuild the connection, and then just the queue doesn't even notice that anything changes in the backend. So and this is very simple idea, and that just applies to the vHost, but in a lot of other different scenarios, that one we can probably see that it's also been leveraged there. And for vHost-user, what we need to transfer is the devices and also the sockets, just to make sure that the FD connection does not break out, and also the new process can just leverage all the virtues to continue to talk with the QEMU, the driver. And basically, this is all simple engineering work. No need to go to all the details, but just one thing to call out here is we need to make sure the handover process very smooth, and to make sure of that, we need to make sure there's only a single operator at one time. For example, the message handling. So just to make sure that we, when we start the migration process, the old one will stop the message handling nicely, and then just do all the transfer, and to make sure that the message handling happens only at one side. Okay, and also is the data path. So we can go to the next. Let's first talk about the message handling part. Um, uh, you know what we can control is during the when we do the upgrade is that we can say, oh, we don't add new ports, and we don't you know do other like maintenance stuff. But what we cannot control is what the guest will do. Right now, the guest can say, I'm going to change the queue numbers, and also maybe the guest will try to restart, you know, or just pull out the driver and insert another driver. So there's going to be a message flow between the host and the QEMU. And in that case, we need to make sure, no matter what the situation is, like there's message handling ongoing, but when we try to do that, the upgrade, we needed to first pause the message handling in the old process, and also the new process need to make sure the message, just to make sure it has a clean state to accept all the transfer, and the old one should create the spread nicely. That so make sure that once it receives the message, it will handle that before it create. And then after everything is done, the message handling can be resumed. And you know, if the process is done nicely, then the new process can just call the function to start the process. But if it fails, the old process can just resume the message handling and pretend nothing just happened. So you know, if you know, if we want to try again, then it's okay to restart the process. And then there could be exceptions. Most of them should be like in some cases the devices are in faulty state. For example, sometimes the negotiation process breakdown, maybe because of the driver, maybe because QEMU, like some other different causes, but there could be. So what we need to do is to really check all the devices before we do the migration, and skip those in faulty state. And for anything else, we can just cancel the transfer. This process may look a little bit complex, but really, if there's anything go wrong, we just need to cancel the transfer and do nothing else dramatic, because you know, the old process is still running, and you know, the transfer just happens. You know, it's not mangling with the data path, so it's just a transfer process, and it's easy, and it's okay to just cancel that. And you know, we have run this like millions of times, but maybe I can just recall maybe 1 or 2 times it's caused by socket failure, but there should be not you know, no other things that's caused the failure. And this solution is looks very reliable. Okay, so let's talk about the downtime, because the way why we do this is to really to minimize the downtime. So just a few tips here, and this is what we learned during the process. First is to we only need to stop for the volatiles, which means the indexes, and everything else we can just pre-copy them, just treat them as sessions and other static stuff, because once you stop persisting the message, then everything becomes static except for the data path. So and we need to notice that the the devices and other sockets, they are huge if you have many ports there. So it takes a lot of time. We can just do the pre-copy, and then make sure the switch happens. The data path switch happens when everything else is ready. We don't need to wait for other information to be ready, such as the NIC, maybe the VTAP or other information. That one can, because once we stop the old PMB in the old process, the network downtime start coming. So that's also some straightforward idea. And then third is to avoid the CPU contention. Basically, when we have two processes designed for the upgrade, we have double copies for like memory, but for CPU, definitely we're going to need only have one, the same PMD. So that makes sure the new process does not start the PMB, before the old one stop. Otherwise, no matter which one is persistent traffic, if you run two PMDs on the same core, you will experience like tens of milliseconds of jitters, and that one can make the guest notice. That jitter is almost higher than the actual downtime of the upgrade itself. And finally, it's suggested to use automated state machine, not use a lot of commands to do the whole process. The state machine can for example, we can show in the process like this is like the state machine, and the blue one are the old process, and the green boxes are new steps in the new process if we use this state migration mechanism. And if we start counting from the old one PMD stops, and all the way to until the new process starts its PMD. Now this is the time period that the network pause. It's not like network down, because the queues are still functioning. The guest can still update the indexes and send packets, but at this time there's no packet persisting in the host. So we need to make sure that every microseconds here counts. So just make sure that it has a very, very tight state machine here. Once we stop the PMD and we sync the final volatile indexes, those states, and then in the new process we just attach the Vhost PMD and we can start the message handling, and then we can fabricate the flow from NIC. And finally, we can start the PMD. And then this picture shows, let me see how many times we have. Okay. And this picture shows the time breakdown of we have two sets of environment. One is like 18 ports, and one is like 255 ports. But we can see that almost other feeds they stay the same, but when we have more vHost port, the final state sync process, which is here, like it increases a lot, and also the vHost PMD config. This part also start to increase when we have more vHost port, but others they almost stay the same. And now the numbers here is microseconds. So although it looks like when we have more vHost port, the time has increased a lot, but if you compare with the old ones, like the second level, this one is still very very good looks. And also we didn't do any dramatic optimization here, because for the state migration, the reliability is a key objective, and the mechanism itself is a big optimization. So we don't need to do more things we don't need to do basically anything smart than that to further reduce the downtime. That's basically that's what we think. But obviously we can try if really needed in the future. And here's the results, the comparison. It's like hundreds of times faster than the natural disconnect mechanism, and also it's very reliable. And the most importantly, it's guest unaware. So and then just 1 or 2 pages to talk about some other maybe not that important stuff. First to think about is the forward and backward compatibility. It's easy to do that across versions. We can easily do that, but the only and it's also fancy stuff to think about. But just need to confirm. Just want to confirm this first. If we really want to develop these features, because when you actually upgrade DPDK versions, it might be also you're likely upgrade other stuff too. So maybe it requires a code reboot of the maybe such as drivers and firmware even. And also we can think about if we want to use like other components to do the transfer, such as maybe the pro buff or anything else. But this is some design choice. Just be careful with if there's more components and more things involved, it's likely to sometimes get in trouble. And the key objective is, of course, reliability. And finally, just one open question: do we want to have it in DPDK? There's no easy answer here. Just if you have it in DPDK, basically it would be good we can have the synergy to improve this, and also people can use this out of box, and it will be supported cross versions. But then you will have more in the future. To maintain this, it's going to cost more effort, and if I don't do that, it's opposite side, right? Okay.
Zhihong, we have a quick question. Before, you want to run through the summary first? I know we're running short on time. I do have a question from an attendee here.
Mm-hmm. Okay.
He asks. This is from Chenbo Jia, and he asks, since this is for OVS Live upgrade, how is physical port handled properly during the upgrade?
Okay, physical port, right? For physical port, it's case by case stuff. If you, when I say case by case, it depends on the NICs, like what the vendor support. For example, you can use different VFs to make sure that the two process can start in the same time, or you can maybe and when you use two VFs, basically you need to switch the traffic between the VFs, right? And then if you use other, maybe you can even duplicate that if the vendor support that. So that's for the physical NICs. Do I answer the question?
That's great. Thank you.
Okay, no problem. Right. Okay, here's a summary. Basically, it's just we talked about, right? We want to solve want to make sure we can have guest unaware, and we can do some rapid iterative development to the virtual switch, and so this solution can be can like run like millions of times without failure, and also it can accept a lot of changes. It has no like other requirement to to the basically the application. So okay, let's thanks. So any more questions? Sorry about the time that we wasted in the beginning.
Any more questions for Zhihong? Got a question here.
Okay, maybe you talked about it, but I didn't hear it, so didn't hear it. Does it involve using a DPDK multiprocess feature actually in order to maintain the state of the NIC, for instance? So is your solution assuming that you have multiple DPDK processes sharing the same DPDK state or not? Because if not, yeah?
No.
No. Okay, yeah. So if the process goes down, the NIC should be turned off, because even if the process goes down, there's a PCI reset function and it just resets the device. So the question is, how do you avoid it?
Because your with let me look at this page. Basically, the old one and the new one just they're started in the meantime, in the same time, and they both have the physical NIC the device open. And you can use VFs, or you can you know if it's I mean that depends on the vendor NIC what the NIC you're using, but
okay, so you mean that those processes are at some point in time they both are active, right? Both processes are
right,
active.
yeah.
So
yeah.
If they connect to the same NIC, do they use the same DMA queues, or the new one is using different DMA queues?
I think that definitely use different DMA queues.
Okay, so you have to reprogram the NIC to direct the traffic from the old DMA queues to the new DMA queues.
Yeah.
And that's why it's case by case basis, because some of the NICs may not be able to do that. Okay. Got it. Thank you.
I think we're about at the limit as far as time. Zhihong, thank you so much for that talk. It was fantastic, and we really appreciate you contributing and putting this together. Thanks. Can we have a round of applause?